Hello everyone, my name is Paolo Frigerio. I'm a PhD student from Polytechnic di Milano. My research activity deals about MEMS micromirrors, in particular the implementation of control systems and circuits for driving linear microscanners. However, today I will talk about a different topic, namely what I will discuss is MEMS-based real-time clocks. I will discuss system-level requirements that need to be taken into account when designing such systems, particularly concerning temperature compensation, and I will show the results of an experimental characterization that was carried out in our lab. First of all, what is a real-time clock? An RTC is essentially a time reference composed of a mechanical resonator and an electronic oscillator. Traditionally, the mechanical resonator was implemented using a quartz crystal due to its very good temperature stability, which can be achieved by proper cut of the crystal itself, also using laser trimming techniques. This results, of course, in a large manufacturing cost, as well as a larger final package, which is not particularly interesting for applications where size is of the utmost importance, such as wearable devices. For this reason, in particular, for the smaller manufacturing cost and the smaller area occupied by MEMS resonator, which also enables system-on-chip solutions, thus minimizing the final footprint, MEMS resonators have been more and more taken into account in the past decades for possible candidates as for substituting quartz crystals. However, the drawback in using MEMS resonators is the poorer temperature stability compared to their quartz counterparts. In fact, for a typical MEMS process, a resonator shows a typical frequency dependence on temperature with a linear coefficient in the order of -30 ppm per degree, which on the overall temperature range of consumer applications ranging from -40 degrees C to 85 degrees C leads to a frequency error within ±2000 ppm. It can be compensated down, as shown in the literature, to a few hundreds ppm by a combination of different devices having opposite temperature coefficients, or by using heavy doping of the structure, as well as selected crystallographic orientations that tend to minimize temperature dependencies, as well as ionization. However, on top of temperature dependencies, process non-uniformities must be taken into account, and they set a larger contribution in the order of 2%, that is 20,000 ppm for a typical MEMS process, and this must be compensated at the electronic level, using a scheme which is very similar to the one sketched on the right, where the main resonator frequency is divided down to the desired RTC frequency in the order of 32 kHz by using a multimodulus divider. This divider is driven by a sigma delta modulator, which is in turn controlled by a common word set by software, where the software actually decides which is the value of the common word to compensate for process spread and temperature variations by properly alternating between the two division moduli. The natural question is if it's really worth to use fairly complicated techniques to reduce temperature variation down to a few hundreds of ppm, if an electronic compensation scheme has to be, however, applied in order to compensate for process spreads. So the purpose of the work is actually to understand what are the say, ultimate limits to the achievable frequency stability only using a purely electronic level compensation scheme. Of course, the final value of frequency stability will depend on system parameters, in particular the value of the division modulus and the number of bits of the modulator. For the value of the division modulus, we can actually derive an upper bound set essentially by process spreads. So accounting for the maximum and minimum expected statistical values of the resonator frequency and knowing the desired RTC frequency, we can derive an upper bound, which for our numbers, that is a frequency of 32 kHz and an error within 2%, results to be in the order of 24. This also sets a limit to the maximum resonance frequency of the MEMS device, which has to be taken into account during the design phase. Concerning the plot on the right, where the division factor is plotted on the x-axis and the number of bits on the y-axis, this limit corresponds to eliminating all of the couple of values highlighted in red. The number of bits of the modulator actually sets the final quantization, and thus is strictly related to the final frequency stability value, so the residual error that will be present at the output of the RTC. Of course, as expected, a larger number of bits results in a smaller error. for example, using the formula that's represented on the slide, and considering a frequency stability of about 10 ppm, it corresponds to excluding all of the values highlighted in blue. Of course, we can't use an arbitrarily large number of bits, because not only because of system complexity, but also due to the limitations in the time required to track temperature transients. And in particular, this is particularly true the larger is the temperature coefficient that we want to compensate. We can derive a formula which links the number of bits to the temperature coefficients and the final value of frequency stability, where we can see that the maximum number of bits is actually inversely proportional to the temperature coefficient. So the larger the temperature coefficients, the smaller the number of bits that we can use in the system. It corresponds to eliminating all of the values highlighted in green, and this leaves with a very small subset of values acceptable for the implementation of the system. Actually, since it is actually easier to implement a division by a factor of G, which is a power of 2, it turns out that the optimal solution is just 1, corresponding to a division factor of 16 for our numbers at least, which corresponds to a number of bits of 13 for the modulator. Then, concerning the temperature sensor, we have some requirements, of course, that depends on the previous parameters, and also set the final frequency stability that we can achieve with such system. One first parameter that needs to be taken into account is the update, the frequency, the refresh rate of the update of the temperature measurement, which will depend on the number of bits. Since the sigma delta modulator converts a digital word into a serial bit stream, of course, the larger the number of bits, the larger will be the time required to convert in the average value of this bit stream the value of the digital word, which is at the input. Of course, this sets a maximum limit to the refresh rate of temperature measurement. It also sets a limit to the achievable resolution. We can actually find a formula relating the final resolution to the TCf, the update rate, and the maximum temperature gradient that we expect our system to undergo. For our numbers and for a temperature coefficient of minus 30 ppm per degree, we derive a minimum frequency stability limit of 3.7 ppm. To which, and considering also the maximum temperature range that we want to compensate on, we can derive actually the number of bits required to encode the temperature information. This number of bits is equal to 9 and is different from the number of bits used in the modulator, which is actually obvious because the most significant bits of the modulator will be used to compensate for process spread, while the least significant bits will be used to compensate for temperature variations. In order to validate the design approach, we designed the MEMS resonator coupled to an ASIC containing the Pierce oscillator for driving the MEMS, the fractional divider, a modulator, and a jitter compensation block in order to achieve a clean output waveform, a low jitter output waveform. All the devices were fabricated by STMicroelectronics, while the temperature sensor and the ADC were implemented on board instead of on the ASIC, and the temperature compensation machine was implemented in software using MATLAB. Using this setup, we were able to demonstrate a frequency stability of those devices within ±5 ppm, thus validating our design approach with an output jitter of 40 nanoseconds, which is compliant with typical RTC implementations for such frequencies. The power consumption of the device, of the ASIC part, is within 700 nanowatts, so our device is also a very low power one. If better performance is required, of course, a more complex technique should be employed, particularly maybe to reduce the native temperature dependence, particularly to reduce the value of the temperature coefficient. However, if the desired frequency stability is above these 5 ppm that we've demonstrated, there is no need to apply more complex techniques than just the simple electronic compensation scheme. To conclude, with this work, we presented some design guidelines concerning electronic compensation in MEMS-based RTCs, where we linked the key design parameters to the final frequency stability values, and we demonstrated the ultimate limit that can be achieved with such a simple system. We demonstrated our design approach by implementing a MEMS resonator and an ASIC, which showed an RTC with a frequency stability within ±5 ppm, validating theoretical expectations. Future work will regard the implementation of the temperature sensor and the ADC on the ASIC, thus realizing a fully integrated solution with a power consumption which is expected to increase up to 900 nanowatts. So this concludes my presentation. I'd like to thank you for attending my presentation. It's been a pleasure for me, and I wish you goodbye. Thank you again.